Hi and welcome to PhD at Living. Today we're going to talk about baking soda and baking powder. What are they? How are they different? How do they work? If you're watching this video in the morning, you could call it the wake and bake video. Come on in. For the purpose of this video, we're going to be talking about baked goods that are leavened. That is, they have a gas foaming agent used in them. This is what creates the rise and height and that nice airy texture in something like a cake. If you have enough time, you can use something like yeast, which will react with the fermentable sugars in your dough or batter, creating carbon dioxide and ethanol. Yeah, that ethanol. Nice! If you don't have that much time, you can use a quicker acting thing such as baking powder, or what we'll talk about first, baking soda. Whether in the Orange Arm & Hammer box or otherwise, baking soda has just one ingredient, sodium bicarbonate, NaHCO3. It's called bicarbonate because it has twice as much carbonate per atom sodium as its big brother, sodium carbonate. So with the carbonate, you can see Na2CO3. There are 2 sodiums per unit carbonate compared to the bicarb has 1 sodium per unit carbonate, so it has twice as much bicarbonate. It's a dumb system, but old habits die hard. In order to get the carbon dioxide out of your sodium bicarbonate, you can do it one of 2 ways. The first is just to heat it. So around 50 C or so, sodium bicarbonate starts to melt, and when it melts, it decomposes into sodium carbonate. You also get a mole of water out of there, and what everybody's looking for, that's CO2. The problem is, you have to put 2 molecules of sodium bicarb in to get 1 molecule of carbon dioxide. The other carbon dioxide is trapped in this sodium carbonate, so you really only get half as much CO2 out of that bicarb as you would through a different process. The other trouble is sodium carbonate can impart kind of a soapy or bitter taste to your muffins, and nobody likes that. The second method to get the carbon dioxide out of the sodium bicarb is to react it with an acid. Now in this case, I'm going to generalize it and just call it HA. That means that the A of the acid, whether it's HCl, H2SO4, HNO3, it doesn't matter, it's going to react with the bicarb all the same. Now I'm not suggesting you put hydrochloric, sulfuric, or nitric acid into your pancakes, but just for instance. Anyway, when I react my acid with my sodium bicarb, what I end up getting is sodium with the A, the conjugate base of that acid, with a mole of water again, and that mole of CO2. Now it doesn't look like I have any extra CO2 like I did with the thermal decomposition method, but I only have to use 1 sodium bicarb to get 1 mole of that carbon dioxide. So if I just double everything and use 2 molecules of my sodium bicarb, I end up getting 2 molecules of my CO2. So this is now a 1-for-1 ratio, where in the previous thermal decomp method, it was a 2-to-1 ratio. Well, great, I know I need an acid, but where can I get one? Well, if you're using a dairy source for your acid, something like buttermilk, sour cream, or Greek yogurt, you can use lactic acid. Now that comes from the fermentation of this disaccharide here, lactose. Remember that? Sugars and stuff? What a great time. Anyway, the lactose ferments and becomes lactic acid here. This, as you'll remember from your organic chemistry, is a carboxylic acid, so we have that acidic proton right there. That'll react with that sodium bicarb and give you your carbon dioxide. You can also cheat this by, instead of using lactic acid, using citric acid. This triprotic acid seen here. Triprotic meaning it has 3 acid groups that can be used to pull off that carbon dioxide from that sodium bicarb. This is what I use for makeshift buttermilk because I usually don't have any lying around the house, so I'll just take regular milk and add lemon juice to it. Stir it around for a little bit and you have essentially buttermilk. If you don't have any of that stuff and are in a real bind, you could just use a little bit of vinegar. It's like a 3% solution of acetic acid. Again, you see this carboxylic group cropping up all the time, and you can use it, but this one is also, keep in mind, the volcano reaction that you saw when you were really young. Vinegar plus baking soda makes a bunch of carbon dioxide. That's what gives you your Vesuvius coming out of there. Pretty cool, huh? And that's baking soda. Keep in mind that if you want to take that sodium bicarb through the pathway that gives you more CO2 and prevents that bitter, soapy sodium carbonate byproduct, you have to have the acid. So keep in mind to have that acid around if you're baking with baking soda. Now on to baking powder. Baking powder is a 3-part mixture of baking soda, no way, a dry acid, and a bulk filling agent. It's basically a one-stop shop for carbon dioxide production that just needs a little bit of water and some heat. The acid is called dry because it is a solid at room temperature. Reactions in the solid state take a little longer to happen than they would in a liquid form, so your dry acid isn't producing carbon dioxide when it's sitting in your cupboard. The bulk filling agent is usually cornstarch and has three specific purposes. The first is to soak up water. If we know with water in there our reaction is going to happen, we want the bulk agent to soak up that water to prevent that from happening until we actually want it to happen. The second reason is for flow. The starch in there prevents things from clumping up, so it's easier to measure and easier to mix into your dough or batter. The third reason is really, as the name suggests, just a filling agent. It pulls up volume so you can measure stuff out more easily. If it was just our baking soda and our dry acid, you'd have to measure out very, very small amounts for a given recipe. Think back to our artificial sweeteners where you have something like sucralose that's 600 times sweeter than sucrose. If you wanted to have the same amount of sweetness in there, you just have to put 1 or 2 little molecules in there, and that just wouldn't be practical. Let's talk about acid, bro. Sweet. Your dry acid in baking powder can be either fast-acting or slow-acting. Fast-acting acids have all their carbon dioxide production within minutes of you mixing them in your bowl. This is something like cream of tartar or monocalcium phosphate. Now, because I don't want to draw out all the chemical structures of these big long things, I'm going to do kind of a cardinal sin in chemistry and just abbreviate stuff really, really poorly. So monocalcium phosphate turns into that, even though the C is calcium where C is technically carbon. Please just bear with me. The slow-acting acids happen a little bit differently, where there's a bit of carbon dioxide production off the bat, but the majority of it doesn't happen until you expose it to the heat of the oven. The slow-acting acids are a little more forgiving because they give you a little more buffer where you don't want to beat out all that carbon dioxide. You put it in the oven, you'll get a little more rise in there. This is something like disodium pyrophosphate, sodium aluminum phosphate, and sodium aluminum sulfate. There's also a category called double-acting baking powders, which creatively just have a little bit of a fast-acting acid and a little bit of a slow-acting acid to combine them and really take all the guesswork out of it. Okay, time for another Stupid Science Adventures with Devin. I read an article on this whole thing that was talking about aluminum toxicity in your baking powder and whether that was going to kill you or not. So let's have a thought experiment. I found an article somewhere that said about 40 milligrams of aluminum per kilogram of body weight per day is about what you should stay under. I was making a biscuit recipe that called out 1 tablespoon of baking powder. I weighed that tablespoon a number of times and came up with 8 grams of baking powder per tablespoon of baking powder. What we're looking for is the aluminum content inside that baking powder. So I looked and I found a relative formula for what the baking powder would be. It was 30% sodium bicarb, 12% monocalcium phosphate, and 26% sodium aluminum sulfate. The fast-acting agent, MCP, and the slow-acting agent, the SAS. This is a double-acting baking powder. Anyway, it doesn't matter. What we're looking for is the aluminum content inside that SAS. So if in the baking powder, the sodium aluminum sulfate is 26%, what's the aluminum amount in that SAS? Well, if you take the molecular weight of the SAS, assuming that it's the dodecahydrate, you get 458.28 grams per mole. And with the atomic mass of the aluminum, 26.98 grams per mole, you end up with 5.89% aluminum in the SAS. Now what we want to see is how much aluminum is in that 8 grams of the baking powder tablespoon. So if you take 5.89% of the 26% of that 8 grams, you end up with only 1.47% of that 8 grams, which works out to 117.6 milligrams of aluminum. Now if you divide that by 74.8 kilograms of Devin, how much I weigh, we're going to end up with the unit that we're looking for, milligrams of aluminum per kilogram of body weight. You do the calculation, what do you end up with? Well, it turns out that you get 1.57 milligrams of aluminum per kilogram of Devin in that biscuit recipe. So 1.57 milligrams per kilogram if I ate the whole effing batch of biscuits, which I might have, but is besides the point. Anyway, 40 milligrams per kilogram, 1.57 milligrams per kilogram, your baking powder is not poisoning you. And there you have it. Dimensional analysis, stoichiometry, action, intrigue, limiting reagents, acid-base chemistry. Bet you didn't think there was that much going on in baking soda and baking powder, did ya? See you next time.